cause autism? Does childhood vaccine schedule overwhelm your child's immune system? Should adults get vaccines? And can vaccines cause diseases that they're meant to prevent? Get the answers to all of the above questions and more. Come learn the story of one of the greatest successes in modern medicine that has reduced or even eliminated diseases that devastated the world not long ago. Enjoy a fact-based discussion on the history, the state of the field, and future developments in this exciting area. So tonight's presentation is led by researcher James Sampson, who is the founder of Breaking Science, a science education organization that strives to engage non-scientists and facilitate their development of scientific critical thinking skills. James earned his PhD in immunology from Tufts University Sackler School of Graduate Biomedical Sciences. Easy for me to say. So let's give a big round of applause to James. Thanks so much, James.
Thanks everyone for coming out tonight. Hopefully I can tell you an exciting, compelling story and keep your interest. So that was a pretty good introduction. I don't think I can introduce myself better than that. I have business cards there if anyone wants more information about Breaking Science and what we do. We go to local libraries and give talks on subjects that people are interested in, science that's in the news, and take this really cutting edge stuff and make it accessible to anyone. So look at our website. If you see a talk that you'd like to see, contact Robert and we'll see if we can bring it here. All right, so the true story of vaccines. I became interested in this topic many years ago, long before I myself was a parent, because I think vaccines are a really fascinating topic. And I get it. There's a lot of scary information out there, especially for parents, right? There's a ton of decisions that you have to make as a parent about what you should be doing, what you shouldn't be doing, and it's overwhelming at times. I'm not going to tell you what you should be doing about the status of vaccinating, but I will give you the science-based evidence and allow you to make an informed decision. So, a disclosure, I do work for a small pharmaceutical company. This one is no longer accurate. I just got a new job. I don't personally make vaccines. I don't have any financial ties to any companies that make vaccines. I'm really just sharing my expertise with you. And I'm not being paid to give this talk. No one knows that I'm here. I'm doing it of my own will. So, what does the word vaccine make you think of? There's no right or wrong answer.
Measles.
Okay, good. Yeah, that's a very common answer. What else? Yeah, sure. Polio is another disease we have a vaccine for. There's no right or wrong answer. We're going to talk about what vaccines are over the course of this talk. So the outline of the talk. First, we'll have to go into my bread and butter a little bit and talk about how vaccines actually work. So for that, we'll need to have a little bit of an understanding of our immune system. Then we'll talk about the childhood vaccines, which are what most people think of when they think of vaccines. And then we'll go into some adult vaccines, because there's actually a lot of really cool developments in that field that a lot of people don't know about. And then we'll wrap up by talking about what's going on to really advance the field of vaccines, both in cancer and, if we have time for it, like a universal flu vaccine. And then ultimately we'll end with a call to action should you choose to accept it. So how do vaccines actually work? Vaccines are drugs. They work by mimicking pathogens, so an infectious agent, but they're weakened in some way that they won't cause an infection in you. The cool thing about vaccines is they allow you to control the amount of exposure and the timing. So I can say I'm going to be exposed to just a little bit of measles, for instance. It's not actual measles in the measles vaccine, but I can be exposed to a little bit of measles that'll give me immunity before my baby is going to be exposed to measles naturally. The earliest vaccines, this is not a great idea, were just live vaccines. So for instance, smallpox, they would just take off a scab from someone and then inoculate another person with it. Not a great idea. It caused smallpox, about 50% of people died, and that was actually the birth of the anti-vaccine movement. I cut out the history section of this talk just in the interest of time, but there's some really cool stuff about how we almost lost the American Revolution because the British soldiers were vaccinating and we weren't. But I'll leave that for another time. Second talk if you guys want it. Now, no vaccines are done that way. They're all attenuated, so weakened, or fully killed where they can't replicate at all. Or if we've done a lot of research and we understand what parts of the vaccines cause protection, then we've made subunit vaccines, which just have little parts of proteins. So how do vaccines work? So here we have a rotavirus. This is actually what rotavirus looks like. It's an electron micrograph. It infects your gut. It infects the epithelial cells that line your gut. It releases toxins that kill them, and then your gut essentially becomes permeable, and you can get really bad diarrheal disease, and it can cause a lot of problems, especially in children. In your gut, you have these resident immune cells called dendritic cells. They're constantly just sitting there, like grabbing stuff and waiting to find something that's not you. So if they encounter an infectious agent like rotavirus, they'll pick it up and say, look, this is something that's not us. We should alert the immune system. So they present proteins from the virus to what are called lymphocytes, so T cells. You may have heard of T cells before in the news. B cells are another immune cell type that can recognize the virus directly. They make antibodies. And the lymphocytes, the T cells that become activated, will kill the virally infected cells, and then you'll resolve your disease that way, or the antibodies will block infection. So vaccines work almost exactly the same way. So here you have a rotavirus that is non-infectious. We've weakened it or killed it. It can cause a primary infection, so it'll go on to infect one cell, but then it doesn't replicate within your cells, and it doesn't produce the toxins that cause the disease. The cool thing about that is your immune system still recognizes it, still presents to your lymphocytes, and then you still get clearance of the pathogen. And your immune system is really good at remembering what it encountered before. So you can get this vaccine as a child, and your immunity will last, depending on the infectious agent, throughout your whole life, or at least a very long time. To summarize, B cells make these little Y-shaped proteins that grab on very specifically to the viruses and prevent them from infecting your cells. And then there are these cytotoxic T cells which release proteins that kill infected cells. We also have a demonstration about herd immunity, which I'm not sure that we actually have enough people in the audience to do, but the concept of herd immunity is basically that you don't need to vaccinate every person in a community in order to prevent massive outbreak. So you can model this statistically. For any disease, we understand the infection rate. So for measles, for instance, the infection rate is really high. It's 90% or above. So with a disease like measles, if you have a 90% chance of catching it, then you can model if you have 10 unvaccinated people around you, 9 of those are going to get sick, and then they can spread it to 9 other people of 10. So it can spread very, very quickly, right? So with measles, you need about 85 to 90% coverage with vaccines, or even better, a little bit higher, in order to prevent a very, very fast outbreak. Some other diseases don't spread so quickly, and you don't necessarily need such a high vaccination rate in order to prevent this from happening. So the herd immunity effect is, if I'm not vaccinated and you are, you're not serving as a reservoir for the virus or whatever it is. So you're preventing a source of infection from me. So, and if anyone has any questions at any point, feel free to interrupt me. So childhood vaccines, what most people think of when they think of vaccines. How well do they work? What are the risks? We'll go into all of these things. So there are a lot of childhood diseases, and they can be very, very traumatic. Not too long ago, polio was a very big problem. It caused paralytic disease in a lot of people. Rubella is another big one. It can cause cardiac problems, can cause blindness. There's a large sequelae of problems that can happen with that. Pertussis is, of course, whooping cough that can also be fatal. And then you have this canonical disease that everybody thinks of because it's in the news constantly, measles. So this causes a rash all over your body. Not a great thing, but it also has a lot of other health problems associated with it. So I'm going to focus on measles for a little bit, just because it's very popular, if you will. But we can talk about any of the other diseases if you'd like. So measles is transmitted by fluid droplets. So if I sneeze on you and I have measles, that's not a good thing. I can be infectious with the pathogen for 2 weeks before I show any symptoms, and 2 weeks after the symptoms resolve. So it's actually a pretty large infectious window. You can feel perfectly healthy and still be able to transmit the disease to other people. And a sneeze droplet, for lack of a better term, can be infectious for 2 hours just sitting around. So if I sneeze on this podium and then someone comes up later at 9 o'clock tonight, they can get measles if I had measles from that. So it's incredibly infectious. One of the most infectious pathogens on Earth, actually. Luckily, in many people that get measles, the major problem is just a flu, essentially a flu, flu-like symptoms. Nobody likes the flu, but it's not the end of the world, right? The problem is that there are a lot of other problems that come along with measles. So 10% of patients, and this is never talked about, will get this really nasty, foul-smelling discharge from their ear that lasts for years after they have the infection. So it can also cause deafness, if you get it in the nerves that handle your ears. The biggest problem with measles is if it infects your brain. So if it causes encephalitis, inflammation in your brain, you can have brain damage. You can die from this. This is the major cause of mortality with measles. But altogether, measles accounts for a very large chunk of morbidity and mortality. And actually, prior to the introduction of the measles vaccine, there were 8 million people every year dying from measles in the world. So along came this guy who lived essentially in all of your backyards, John Enders. He was a physician at Harvard. He had the great idea to go into boarding schools in Boston and find kids that had smallpox in the 1950s. He went into schools and got measles from kids. He took the measles virus, which really only infects humans, and he tried to force it to infect chicken embryos. So as I mentioned, the measles virus is specifically adapted to humans. So in order to infect the chickens, it had to mutate, which caused essentially a loss in the fitness of the virus. It can't infect humans as well. Not so good for the chicken, good for us. So this is how we get attenuated or weakened viruses historically. He then took this weakened virus and inoculated monkeys with it. He challenged the monkeys with full measles virus, like infectious measles virus, and they were almost 100% protected, which was really great. The thing that's a little bit insane, and I'm very confident in my own work, but I'm not sure I would ever do this, is he took his attenuated virus and essentially vaccinated himself and some of his consenting colleagues, and then infected himself and them with measles, and they were protected, luckily for them, because otherwise that would have been a pretty big legal issue, I think. But so this was the story of the development of the measles vaccine. But it goes further. So John Enders was a very socially minded scientist. He realized that his vaccine had some side effects. It caused a fever. It was not so great. So what he did, it also caused a rash, looking a little bit like measles. Not great, right? He freely gave out his attenuated virus to anybody that wanted it, pharmaceutical companies, universities, and he said, try to make this better. Let's get this to be the safest vaccine we can before we actually put it into distribution in people. So Merck picked up the virus, and in a move that would be completely uncharacteristic of modern Merck, they spent a lot of time and energy reducing the side effects. And they did a pretty good job of it, actually. So in 1963, the first measles vaccine was licensed in the United States, and less than a decade later, it was combined into the MMR vaccine, measles, mumps, and rubella. So how well does this vaccine actually work? Really well is the answer. 2 doses of the MMR vaccine cause protective immunity in 99% of people. That's one of the best vaccines that we have. Measles incidence in the United States, up here is before the vaccine was introduced. There were about 500,000 cases in the United States per year. And then the vaccine was introduced, and it dropped precipitously immediately. Within a couple of years afterwards, you had less than 50,000 cases per year, which is a 90% reduction very, very quickly. And you can see that it stayed low and continued to get low through the 90s, when there were essentially but very, very few cases, hundreds of cases rather than thousands of cases per year. Unfortunately, vaccines are victims of their own success to some extent, right? If you are vaccinated, what happens is you don't get the virus, you don't get a disease. Nobody's going out and saying, yes, I didn't get the disease. They just go on with their lives, right? So for a long time, people started to think, okay, maybe we don't need to give the vaccine so much anymore because it's essentially gone. So vaccination rates decreased, and then in the mid to late 2010s, It's been spiking, and you see this in the news with recent outbreaks in New York and some in California and places that the vaccination rate is low. Still, there are not a lot of cases of measles in the United States every year. This is a wonderful thing, but the fact that it could be gone and isn't is a little bit unfortunate. So there are only hundreds of cases per year. Worldwide, measles is still a very, very big problem. There are a lot of places like Africa and Southeast Asia, the Middle East, where the vaccination rate in children is still only about 50%. And so, hundreds of thousands of kids still die every year, which is a terrible problem. But it's a big public health problem trying to get vaccines to these places, and then occasionally there are cultural issues that make it difficult to get people to vaccinate. Measles vaccine is not the only vaccine we have for kids. There are a whole host of things. The reason that kids or babies are very, very susceptible to infection is because you're not born with a fully formed immune system. It continues to develop over the first 6 months of your life, so you're susceptible to a lot of infections that you wouldn't be later. The cool thing is, you can give the vaccine prior to when you would be exposed. Like, most babies are not, wandering around the New York subway when they're 5 months old. Maybe some are, but not all of them. But you can vaccinate before you would likely be exposed to these things. So we have a whole list of things that the CDC currently recommends vaccinating against. And you can look at that and say, wow, that's a lot of shots. Or you can look at that and say, wow, that's a lot of diseases that my kid isn't going to get. So you can go to the CDC website. They have a nice, handy little chart about when you should be getting these vaccines and how many boosters you should get. They also have references to the studies that demonstrate the safety and efficacy of these vaccines at these time points. So if you have any questions about that stuff, I would highly recommend looking at their website. Childhood vaccines can come in multiple different forms. Some of them are oral, such as the rotavirus vaccine, and some of them are intramuscular. Babies generally don't like vaccines that much. The oral vaccines are not so bad because they have a little glucose in them, and that's not so bad. But the intramuscular ones, they scream a lot. This is my son right here, so I can tell you he absolutely hated it for 4 minutes, and then he was totally done crying, and he hasn't been sick since. Well, not with any of those terrible infectious diseases. So how well do other vaccines work? The answer is also really quite well. For instance, diphtheria, most people don't even think of diphtheria ever anymore, right? It's because prior to the introduction of the vaccine, there were thousands of cases of diphtheria in the United States every year and thousands of deaths. Now there are none. After the introduction of the vaccine, there are no more diphtheria deaths in the United States anymore. And you can look, the vaccines for most of these childhood diseases are over 90% effective at preventing infection at all, and almost 100% effective at preventing deaths. So even if you do get the disease, you don't get a severe form of the disease. There are some vaccines that don't work as well as some of them, as others. The Hep A vaccine is not 100%. The Hep B vaccine is not 100%. We're working on them. But again, and if you will, the worst vaccine that we have currently is the pneumococcal vaccine. Only prevents 34% of cases, that's flu, but it prevents 25% of the deaths in children. So it's not a perfect vaccine, but if I had a chance to reduce 25% chance my likelihood of dying from something, I personally would take it. Again, you do what you want to do, but it is what it is. But yeah, so we're actively working on a lot of these vaccines. So how is a vaccine added to the schedule? That's something that not a lot of people think about, right? It's not just that I come up with a vaccine in a lab and then I say, let's vaccinate everybody. So the first step is, just like any other drug, you need safety and efficacy testing preclinically in animals first. So you have to show that it works and it doesn't kill the animals. Step 2, you have to go through the normal 3 phases of human clinical trials, just again like any other drug. So you have to prove that it's safe. You have to prove that it's effective. And the phase 3 trials are with thousands and thousands of people over years. So they're very large. So if you pass those steps, then you'll test in the combination with other childhood vaccines that are currently administered. because you could make the argument that maybe, you know, giving a healthy person just this one vaccine is fine, but then if I give them 10 vaccines at the same time, there'll be a safety concern. So you have to test in combination with what's already there. So let's say you pass those 3 steps. The CDC then has to decide if it's sensible to give the vaccine and when it should be given. So if you come up with a vaccine for space virus, which is a virus that I made up but exists only on the moon, even if you have a fantastic vaccine, the CDC is not going to add it to the schedule because most people currently are not traveling to the moon, as much as my wife would love to. Not because of me, she likes space. So then finally, even if you pass all of those steps, the CDC then evaluates all vaccines every year based on all current available safety data. So, you know, if I gave my son vaccine X and he got a high fever, I can report that to the FDA or the CDC, and then they'll take that into consideration every single year. Just because something has historically been safe doesn't necessarily mean that, you know, if some new safety concern comes up, that it won't be axed from the schedule. So, the CDC estimates that 20 million cases of disease and 42,000 deaths in the United States alone are prevented by vaccines. And for those of you that are financially minded, which many people are, there are $69 billion in cost savings as a result of vaccines, both in direct costs, such as, you know, treating the patient that gets a disease, and indirect costs, like if I got sick, I would have to stay home from work, or if my kid got sick, I would have to stay home from work. So financially, it makes a lot of sense, as well as just public health-wise. So I had a nice video in here. This was from a presidential candidate in 2016. I won't name the person because I'm really not trying at all to be political, but this person hit essentially 4 major talking points that we'll cover that are the major talking points that most anti-vaccine people will use. You know, and this person, based on their financial status and availability of scientific advisors, should have access to all of the cutting-edge research, but yet still made these points. So let's just talk about what those points are. Number 1, are we overwhelming babies' immune systems? A very common emotional reaction to childhood vaccines is, oh, you're giving them, you know, a giant horse needle or something, and you know, putting in so many different things at the same time, that's got to overwhelm them, right? So let me ask you guys, how clean is this room? Nothing personal to the library, but how clean is any given room that's not a sterile room? Yeah, there's all sorts of stuff in this room. Even if we were in my lab and, you know, we were in the cleanest room that we have, there's still bacteria all over your skin, there's still viruses, there's fungi. Like, we don't live in a clean environment. Your immune system is constantly being exposed to many, many different things, and it's hardwired to do this. If you couldn't respond to more than one thing at a time, you would quickly die from an opportunistic infection. So just on principle, we're not overwhelming the baby's immune systems, but to give you some evidence as well, babies that get a vaccine while sick can still clear the sickness. So even if it's an irrelevant sickness, if my baby has a cold and I give him a measles vaccine, he has no problem clearing the cold. Combination vaccines give exactly the same immune response as giving the individual vaccines. So if I took MMR vaccine and I, you know, gave measles, mumps, and rubella individually, you'd have exactly the same level of protection. So you'd think that if you were overwhelming the baby's immune system, the individual vaccines would work the best. It's not the case. And in perhaps another bit of strong evidence, there was a very large randomized control study in Germany. So this is the gold standard of clinical testing, where they took thousands of babies. Half of the babies they gave vaccines at 2 months, and then half of them, which was the recommended time for whichever vaccines those were, and then half of them they gave at 3 months, so a slightly delayed schedule. So babies that got the vaccines on the delayed schedule actually had more illnesses overall, not just the illnesses that they were vaccinated against, but more illnesses overall than babies that got the vaccines earlier. Now, from an immunologist perspective, this makes perfect sense. There are things in vaccines that non-specifically boost your immune system. We'll talk about those in another couple slides. So if you are vaccinated, they can boost your immune system, which makes you better able to respond to any pathogen. So, pretty clear that we're not overwhelming the baby's immune system. And even in the past 30 years or so, we've more than doubled, I think tripled, essentially almost tripled the number of things that we vaccinate against, and dramatically reduced the amount of things that need to be in the vaccines. So there were, for instance, in 1980, 15,000 proteins in all of the vaccines that you would get. It's just a number, it doesn't really mean that much. But now, there's only 173. So that's a 100-fold reduction in the amount of proteins. We've covered 2.5-fold more diseases. We're getting better at understanding how to make these things good while only giving what we need to. We're doing everything we can not to overwhelm the baby's immune systems. Do vaccines cause autism? Because this is, of course, one of the major things that people say when they're skeptical of vaccines. Where does this come from? There was a guy, Andrew Wakefield, a physician in England. In 1988, he published a paper in a very reputable medical journal, scientific and medical journal, called The Lancet. In his study, he had 12 kids, so a very small study, and he found a correlation, not a causation, between MMR and some kids developing autism. The news, as they do, picked this up and ran with it. All of a sudden, this study became, vaccines cause autism. There's a very important distinction between these two things are correlated and this causes this. And vaccination rates dropped because people were afraid of giving their kids autism. Several years later, Andrew Wakefield was stripped of his medical license for scientific, ethical, and medical misconduct, and the paper was retracted. So when a paper is retracted, it's not just that we've come up with more data and we understand the conclusions in a different way. No, this was never supposed to be available to the scientific community because it's founded on non-science. Very, very different from the self-editing process that science normally has. The closest that anyone has ever come to even the worry that vaccines may actually cause autism is that in 1999, the American Academy of Pediatrics asked that we switch to single-dose vaccines instead of multi-dose. With multi-dose vaccines, we have to put in a preservative. It's called thimerosal. It does contain mercury. And it was unclear whether specifically thimerosal, caused any potential autism. Let me tell you a little bit about thimerosal. So there are multiple ways that you can get mercury into your body. It's true, mercury is not a good thing to have. Methyl mercury is present in fish. Methyl mercury will deposit into your body and accumulate and can cause problems over time. People still eat fish, right? It's not the end of the world. Thimerosal is ethyl mercury, so it's a different form. It doesn't deposit in your tissues like methyl mercury does, and it's excreted by the kidneys much faster. So not only is the amount of thimerosal in vaccines vanishingly low and much lower than you would get from eating fish if you regularly eat fish, it's not as bioavailable as the type of mercury that's found in fish. So, don't take my word on that. There have been many, many meta-analyses, so people looking at all of the available data with now way more than 1.3 million kids, and they found that there is absolutely no association between autism, MMR, thimerosal, vaccines in general, or mercury. What does cause autism? I don't have the answer, no one has the answer. But if you guys do, please let me know. I think we could make a lot of money if we knew that. It's not actually clear. There's definitely some genetic factors. There are some maternal environmental factors, so epigenetics plays a role. We don't know what actually causes autism. And so it's compelling to be able to have something to blame, right? But please don't. Another argument against vaccines causing autism is that the first clinical signs of autism appear in a baby at 2 months. A trained pediatrician can diagnose autism at 2 months. That's very long before the first MMR dose is given, which it occurs at 1 year. So, anyone have any comments or anything? Another common criticism of vaccines. I hear there's aluminum in vaccines. So there was this guy, Robert Sears, another physician. And this is actually his picture. It's not just a stock image, even though it looks like it. Probably should be. Yes, we know there's aluminum in vaccines. We put it there specifically. It's been in vaccines for 70 years. Remember those compounds in vaccines that I mentioned earlier that non-specifically boost your immune system? That's what the aluminum is doing. So we take aluminum, we emulsify it in oil, just a very, very small amount, and then we put that in the vaccines. That's actually necessary to get full efficacy of the vaccines. It would be great if we had, it's called an adjuvant. It would be great if we had a better adjuvant. There are no other FDA-approved adjuvants currently. So maybe in the future we can swap the aluminum out of the vaccines, but currently we can't. How much aluminum is too much, or how much aluminum are there in vaccines? At birth, baby comes out of the mother with 0.4 milligrams of aluminum in their body. By 6 months, the baby will have accumulated 6 to 10 milligrams of aluminum, and then after 6 months-ish, they'll start eating solid food. Solid food has a ton of aluminum, and it goes up exponentially. The amount of aluminum in all of the vaccines that the CDC recommends that you get in the first year combined is 4.2 milligrams in the entire first year. So by 6 months, the baby, just by existing and eating, has accumulated more than tenfold, up to 30-fold more aluminum than they would get from just the vaccines. And no one is suggesting that you don't feed your kid. I'm definitely not suggesting that you don't feed your kid. So Robert Sears recommends a delayed vaccination schedule that would give you less aluminum per time and spread it out over time. He calculated the maximum dose of aluminum that you could tolerate because, again, yes, it's true, aluminum is not a good thing to have in super high quantities. The problem is the maximum tolerated dose that he calculated was based on people that didn't have functioning kidneys. They were on dialysis. So the kidneys are involved in excreting aluminum, so they can't tolerate as much. These patients were also given aluminum directly into their veins. So not super relevant to the bioavailability of the aluminum that you get in food or vaccines. What are the actual risks of vaccines? Because I'm not going to pretend that there aren't any. I also want to mention that everything that I've cited here has largely been either from the CDC or other scientific sources that you can find on government websites. If you, for some reason, don't trust the government and don't like pharmaceutical companies, there's this Institute of Medicine of the National Academies. They're an independent group, they're an NGO, they don't hire any pharmaceutical employees. So even though I don't work on vaccines, I wouldn't be able to get a job with them. And they publish safety and efficacy data, and it's largely in line with what the CDC says. So the MMR vaccine has been out for more than 40 years, it's a long time. We have a lot of data about how safe and effective it is. There have been at least, and I made this talk a couple years ago, 60 studies done on 15 million kids. It's more than that now, especially with the recent attention that measles has been getting. So risks of the MMR vaccine. 1 in 7 kids will get a fever. 1 in 20 kids will get a mild rash. Risks associated with measles. 1 in 20 kids will get pneumonia, and 1 in 1,000 kids will get encephalopathy, so inflammation of the brain. Risks associated with the MMR vaccine. 1 in 4,000 kids get febrile seizures. These things are terrifying. The kid will start to shake, but they're not medically dangerous. And they happen pretty much any time the kid gets sick. And 1 in 40,000 children will get temporary clotting problems. With mumps, if you're infected with mumps, the risks of that are 1 in 7 kids will get meningitis, and 1 in 2 will get testicular atrophy, which hopefully I don't need to explain. It's not perhaps something that you would want to get. Another MMR vaccine risk. 1 in a million people have an allergy to an ingredient in the vaccine. This is the case with essentially all vaccines, right? If you get rubella, within 20 weeks of pregnancy, so in the first trimester essentially, you have 100% risk of either miscarriage or birth defects. So that's not great. So just keep in mind, everything that we do in life comes with risks, right? Feeding your kid, you could feed the kid, they could choke on it. It's up to every parent to decide what is a tolerable level of risk. But it's also important to make an informed decision about what are the risks of getting the vaccines and what are the risks of getting the natural infection. So, less doom and gloom. Let's switch over to the adult vaccines. Any questions on that stuff so far? Okay, adult vaccines are pretty cool. Most people don't think about adult vaccines, but there are a lot of them, and they can be very helpful. So this is the CDC recommended adult vaccine schedule, and I'd like to point out that vaccines in adults work better earlier. The older you get, the more your immune system declines and the less efficacious vaccines are. So if you don't have these and you want to get them sooner rather than later. So you can read the list. It's on the CDC website. There are a lot of different things that we vaccinate against. Influenza is perhaps the one that everyone thinks about, and also perhaps the least efficacious of them. But you can get MMR boosters. HPV is another one. It's come out in the past, certainly within the past 10 years. This is our first actual anti-cancer vaccine. It's not really anti-cancer, but it's against the infection that causes cancer. The CDC is now recommending this both for boys and girls because it's silly to only vaccinate girls. But yeah, so this can prevent cervical cancer, which is really kind of cool. And then there's a laundry list of others. We'll talk about some of them specifically. So a really cool case study is shingles. So shingles is caused by the same virus that causes chickenpox. So if you get infected with chickenpox when you're a kid, which I wasn't, I was born before the chickenpox vaccine was out, so I got chickenpox. I could later on, once I become 50 or above, have shingles. So 1 in 3 Americans will develop a case of shingles, and the risk increases with age, 50% of people over the age of 85. So shingles can cause some things that are not so bad and some things that are really not great at all. So you get a rash, again, not the end of the world. You can get pustulant blisters, not ideal, but you can live with them. One of the big problems is postherpetic neuralgia. So this is nerve pain. The antiviral treatments that we give for shingles really don't do anything about this pain. My mother had shingles and she said it was excruciating. I hope to not get it when I get older. So that's not a good thing. If your eye isn't affected, it can cause blindness because the virus that causes this disease essentially just travels through your nerves. If it goes into the trigeminal ganglion, it can cause blindness. It can also cause hearing loss if your auditory nerves are affected. And then, of course, encephalitis. You have a lot of nerves in your brain, so it can cause inflammation in your brain. And the current treatment is, like I said, antiviral drugs. They don't work all that great. It's better just to not get the disease. So we have 2 different shingles vaccines. One that came out several years ago is Zostavax. This is a pretty decent vaccine. It's a live attenuated vaccine, so it's weakened. It will infect you, but not spread. It works for about 3 years, and it works for about 50% of people that get it. Importantly, elderly, I believe around 85 years old, the vaccine doesn't work very much at all, and these are the people that are most at risk for getting shingles. Just for your information, in case anyone's looking to get it, even without insurance, this vaccine is $122. It's definitely covered by Medicare Part D, so it's up to you if you want to receive a course of antiviral drugs and still have nerve pain, or you can just pay that out of pocket or with your Medicare. Even better, there's a more recent vaccine called Shingrix. It was approved just 2 years ago now. It's an adjuvanted subunit vaccine, so just a very small part of the virus. There's no risk that it will go latent in you as a result. And it works for longer, 3.5 years. And importantly, it seems to work in 90% of people, even in elderly people, which is great. Slightly more expensive, but it's also covered by Medicare Part D. So we are actively working on these things, making them better all the time. Question for you guys. I haven't entirely given you enough information, but see if you can work your way through it. If I've had a chickenpox vaccine, do I need the shingles shot?
Is that an attenuated virus?
That's the question that you needed to know. Yes, so the chickenpox vaccine is an attenuated virus. So it can, in some small subset of people, it will infect your nerves and then can reactivate when your immune function declines. So yes, it is actually advisable to get the shingles vaccine until we come up with a better chickenpox vaccine. Yeah, that was a good question. Okay, new concepts in vaccination. We're not just a stagnant field doing exactly the same thing, taking a weakened pathogen and sticking it in some aluminum and sticking that into people. We're doing really cool stuff, I promise. So we'll start by talking about anti-cancer vaccines, because those are really hot right now. We have 2 anti-cancer vaccines currently. I think I misspoke earlier saying we only had one. Hepatitis B vaccine and HPV. So both of these induce an immune response against viruses that can then go on to cause cancer. So they're prophylactic cancer vaccines, but if you have cancer, they won't do anything for you. So there are some therapeutic cancer vaccines that are on the market or coming up in trials currently. So I believe the only FDA-approved one currently, unless there was one very recently, is for metastatic prostate cancer. Not a lot of options for patients with prostate cancer, so this is a great thing to have. It's called Siblucil, and it boosts the immune response that you already have going on, so you can clear the tumor. The way it does this is it tries to identify what are called neoantigens. So tumors are essentially you, right? That's one of the things that make it really difficult for your immune system to fight tumors. But every now and then a tumor will pop up with a mutated version of a protein that you would have had, or a protein that it shouldn't be expressing, and these are called neoantigens. So we can mount an immune response against those because they're the most different from your normal tissue. So there are 3-ish approaches that are being tried currently for anti-cancer vaccines. One is to just take these neoantigen proteins directly and stick them in your body. It doesn't work all that well to do that, mostly because they're cleared very quickly. The second approach here is the one that I just mentioned, where you'll take the patient's blood, pull out those dendritic cells that I mentioned earlier, the ones that are just waiting to pick up foreign stuff, pulse them with the neoantigens from the tumor, and then put them back into the patient and hope that they boost the anti-tumor response. So that's a neat approach. It's not having amazingly great success as a monotherapy currently, but we are working on improving that. And then there are essentially next generation approaches where we use biomaterials engineering. I'll give you one example of those. So here we have essentially a vaccine delivery unit. We have the protein that we're trying to immunize against as the red thing trapped in the middle of this. We have a nanoparticle, the white stuff, coating it, and the nanoparticle won't break open unless it's in a very acidic pH, so your body is mostly neutral. And then decorating the surface of this, the little blue things are adjuvants like the aluminum that will boost the immune response. So you stick this into a patient, dendritic cell picks it up, they eat it, and after they eat it, they digest it, which involves acidification. So the nanoparticle breaks open, and all of a sudden, all the red proteins that the tumor proteins, are stuck on the outside of the dendritic cell, and you activate the immune response just like you would normally. So those are currently not in trials. They're still in preclinical, but hopefully within the next couple of years, they'll be tested in patients. All right, finally, we got a couple minutes left. We'll wrap up with the universal flu vaccine quest. Nobody likes having to go to the doctor every year to get a flu vaccine, even people that like the flu vaccine. Why can't we just make a vaccine that works against all of them and you don't have to go back to the doctor for? The answer is because it's really hard. We are doing our best. So this is what the influenza virus looks like. It has a very complicated set of proteins on the surface. It's an RNA orthomyxovirus, for those of you that were interested. There are 3 major families of influenza virus. One of them is the major one that infects people every year, that's group B. One of them is incredibly rare, so we don't really have to worry about it, that's group C. And then the group A mostly infect animals, but when we have a pandemic, the influenza virus mutates, switches over to being able to infect humans very suddenly. Those are the group A viruses. And importantly, there are 2 proteins on the surface called hemagglutinin and neuraminidase. These are important to get the virus into and out of your cells. These are, when you hear like H1N1 in the news, that's defining which version of hemagglutinin and neuraminidase that you have. Why do I mention those? Well, because we're trying to target them, but I'll talk about those in a couple slides, never mind. RNA viruses such as influenza mutate very rapidly. Influenza, essentially every time it replicates, it has 1 mutation in its genome. By comparison, every time one of your cells mutates, there's no mutations. It takes like thousands of replications in order to have any mutation. So this is a very rapidly changing virus. So that's one of the hurdles. The biggest way it can change is the influenza virus essentially has 8 chromosomes, like us. If you're infected with 2 different influenza viruses at the same time, they can swap chromosomes and then suddenly be very, very different and make a virus that you've never seen before. So even if you had immunity to this one, or this one, if you have a partial immune response to both, they swap, they make some new things, you have a new virus that you're not necessarily immune to. So why doesn't our current vaccine work better? Well, mostly we get an immune response to this blue thing that sticks out for the furthest on the virus. It kind of makes sense, right? That's what you would see first. That's the hemagglutinin. The problem is the head of the hemagglutinin is incredibly variable. Viral species to virus species, it's very different, and it mutates a lot. It would be much better if we could target the red stalk region, because it doesn't change a lot, or the neuraminidase, which also doesn't change a lot. The problem is original antigenic sin. So this is a concept that not a lot of people think about. The first flu virus that you respond to is going to be your dominant response throughout the rest of your life, right? Not necessarily throughout the rest of your life, but it'll be the major response until you get really hit by the same serotype a lot. If I'm first infected with H1N1, and then I'm later infected with H5N9, I just made that up, my immune response will partially be to H1N1 no matter what, and that doesn't necessarily protect against the second form. So if we could make a childhood vaccine that targeted one of these like non-changing parts of the virus, that would be the ideal thing. So how do we do that? Like I said, we target the stalk of the hemagglutinin, we target the neuraminidase, and there are a couple other like surface proteins that don't really change that much. The problem is none of these are very immunogenic. The immune system isn't very good at recognizing them. So we have to engineer like new ways of making them immunogenic and dominant in the immune response. So it's not so easy. Call to action, should you choose to want it. Be very, very careful about information that you take in about vaccines, or about anything for that matter. There are entities out there, like this group, the Children's Medical Safety Research Institute. That name sounds really super nice, right? And they have a nice little website with children playing, so you think they're looking out for kids and stuff. The problem is they have a ton of memes, like this here on their website. New study finds corrosive debris hidden in vaccines, and they have this giant, I've never seen a needle like this, but it is what it is. And of course the skull and crossbones, because that just adds to the touch. I would be incredibly skeptical of anybody that advertises to you using memes. If the CDC did that, I would recommend the same, but they don't. They also have a bunch of papers on their website that have been withdrawn, like they're no longer part of the scientific body of literature, but for some reason they neglect to tell you that, so be skeptical of that. Be very careful about what you share. Facebook is a terrible source of information about vaccines and a terrible way to have discussion about them. I'm generally anti-Facebook anyway, but it's too easy for memes and name calling to happen. Even news sources aren't always 100% reputable, right? So this is a random newspaper that I found from Toronto. And it's talking about the hidden dangers of Gardasil, which is the HPV vaccine. So if you dig into the scientific literature, this is actually a non-issue. But the scientific reporting with this particular newspaper, which may be a tabloid, I'm not actually sure, is insufficient. Yeah, I mean, there are a lot of things out there like that. Best sources that I would recommend, PubMed is a really good database of all scientific literature. You probably don't have access to most of the papers at home, but usually libraries will be able to give you access to any of the papers. The CDC will break down any of this information and give it to you in a more reasonable way. And then, of course, there are independent agencies, and that's all if you don't trust me. I guess I can't tell you to trust me, but you should trust me. So if you want to be what I refer to as a Vaxevangelist, someone who convinces people that vaccines are safe and effective. I have a patented 6-step program. It's not actually patented, but it should be, for how to do this. Number 1, don't be a jerk. If you're trying to win any argument, or not win an argument, if you're trying to convince anyone of anything, you're never going to do it by being a jerk. Number 2, familiarize yourself with the scientific peer-reviewed literature that's accepted by the scientific community. You've come here today, you've heard all this stuff. I'm not the only source out there. Look for good sources online and use those as evidence. Number 3, don't be a jerk. Being a jerk is never a good thing. Number 4, empathize. I've spoken to, I can't tell you how many people. I've given this talk everywhere, right? Like, there are vaccine skeptics, there are anti-vaxxers out there, and all of them have the same thing at heart, right? They all want what's best for their kid. They're all worried, and I get it, especially as a parent. I understand it's very overwhelming. Like, there can be a lot of terrifying information out there. So by being confrontational, you're really not helping anything. Number 5, have discussions face to face. I can't emphasize this enough. It's always better than, typing something online. And number 6, don't be a jerk. This is just a really good piece of advice, I think, in life. So with that, I'd like to thank you and ask if anyone has any questions. Yes?
I'm old. When I was a kid, I never saw autism, not like today. Nothing. How do you explain it?
Okay, so I'm going to preface this by saying that I am not an MD or anything like that, so I don't have the hard and fast answer for you about autism. But autism as a disease has only begun to be appreciated recently, right? So behaviors that we now recognize as autism were chalked up to, oh, it's just that kid being weird or something, right? It's true, clinical diagnoses of autism have increased dramatically in the past couple decades, and a lot of that can be explained just by awareness of the disease and understanding that it is a disease. How else could cases of autism increase? Again, because we don't understand the underlying causes, I don't know. The problem is the symptoms of autism tend to appear right around the same time to untrained eyes, right around the same time that you get the MMR vaccine, right? So that's a correlation. Both of these things happen at the same time. It doesn't necessarily mean that one causes the other. I mean, I could have gone to a water park the day before and then my kid is nonverbal afterwards, and I might make the argument based on my evidence, which is an N of 1, like a sample size of 1, that going to water parks causes autism because the two appeared temporally very close to each other. It's just a fact of when we need to give the MMR vaccine, right? Like it happens to be right around when most parents notice that their kid is not socializing like other kids and things like that, which occur at around a year. There is actually some evidence to say that MMR could be given earlier at 6 months and still have efficacy. You need an extra dose then. But I think that would help alleviate some of the worries that parents have about the timing, right? About it appearing, the vaccination happening right around when the symptoms of autism tend to appear. But now I'm starting to appreciate this because my kid is almost exactly 1 year old. Like that's when they start to become sociable. That's when a parent would notice that there's a problem. So I have no answer for you about why autism is on the rise. Yeah, it's probably on the rise. Some of it is an increase in diagnosis, but I, without understanding how the disease happens, I can't tell you. I can tell you that it's not vaccines, though. But yeah, any other questions? Nice. Thank you, everyone.